All right, this will be the final part in this lesson series on the history of atoms and molecules. At this stage, we've learned that stars are responsible for making all the different kinds of atoms on our periodic table. It's now time to tell the story of how atoms can link up to form molecules. The example we use is a very important substance on planet Earth, water. Well, of course, water can exist as a gas in the atmosphere or liquid like in the oceans and lakes, and solid phases like the ice you see here in Iceland. Why is water so important for us? Well, because as far as we know, life is dependent upon water. Inside every cell, every living thing on Earth is composed of cell, and the fluid inside the cell is water. And water is really important for permitting and allowing chemistry to happen within the cell membrane boundary. So in the top left here, we see a little molecular kit version of a water molecule. The little blue plastic piece is an oxygen atom, and the two white ones are hydrogen, and the pipes are chemical bonds linking the atoms together to form a molecule. So the water molecule can be written as H2O, two hydrogen atoms and one oxygen atom. And its structure would be what you see over here. Now in the center here is another way of drawing the structure of the water molecule, but now showing the subatomic particles. So this would be the nucleus of the oxygen atom, 8 protons and often 8 neutrons. And then we have 8 electrons in blue around the nucleus of the oxygen atom. The hydrogen nucleus, you'll recall, is just 1 proton, and that atom has 1 electron. But what we're showing here in this picture here is how the hydrogen atom and the oxygen atom have made a chemical bond. These 2 electrons, we describe the situation by saying that the 2 atoms are sharing a pair of electrons, and that's what we're calling a chemical bond. And the effect of this sharing of electrons is that it's linking these 2 atoms together. So atoms can connect with each other when the circumstances are right that they can share a pair of electrons. Let's see how this might happen. And from last lesson, you'll recall we'll have lots of different kinds of atoms being produced by supernova and ejected out into space. And when the nuclei of these atoms capture their electrons, then we have the full-fledged atoms. Let's imagine we have an oxygen atom and a hydrogen atom, and they're on a collision course. So let's see what happens when these 2 atoms collide. Here comes the hydrogen atom on approach to collide with the oxygen atom. When they get close enough, the electromagnetic force is going to start to repel them. Why is that? Because we have electrons around the hydrogen nucleus and we have electrons around the oxygen nucleus, and electrons are negatively charged. So we have like charges experience a repulsive force. But if this hydrogen atom has a lot of momentum, right, so it's going to overcome that force and get even closer. But as it gets closer, the way the math works, the force gets bigger. But what if the hydrogen atom has so much momentum, this collision is so vigorous that it can get really close to the oxygen? Well, that's when we get the formation of a chemical bond. Now, why is that? Well, when the 2 atoms get really close, the nucleus of the oxygen atom can start to attract the electron in the hydrogen, and the hydrogen nucleus can start to attract the electron in the oxygen. This has the effect of linking these 2 atoms together. So we follow these 2 electrons. This electron now, because of the attraction to the oxygen nucleus, it will spend some time orbiting the oxygen nucleus as well as the hydrogen nucleus. And this one, because it was attracted by the hydrogen nucleus, it will spend some time orbiting there, but then it will also go back to the oxygen. So this arrangement then has the effect of linking these atoms together, and we call this then a chemical bond, the sharing of electrons. So this is just one simple example of how atoms can combine to form molecules. But remember, we have that whole periodic table, all those different kinds of atoms. Well, they can combine in a myriad of ways to form different kinds of molecules. So here we have the situation on the left where a star went supernova and blasted out all these different kinds of atoms. So the nuclei get blasted out, right, and then they capture their electrons. But as these different kinds of atoms interact, they're going to be forming chemical bonds with each other. And so here we have another situation, the laws of nature, that atoms have a certain structure that allow them to link up, to bond with each other, to form new kinds of things. So new molecules are emerging in our universe because of these laws of physics and chemistry. Well, what do we have over here? Here we have two hydrogen atoms colliding, and they form a chemical bond. And that makes the hydrogen molecule, a sharing of a pair of electrons. This molecule is methane. One carbon atom is making 4 chemical bonds with 4 different hydrogen atoms. Here we have ammonia. One nitrogen atom is making 3 chemical bonds with 3 different hydrogen atoms. This is carbon dioxide. Notice the carbon atom here is making 2 chemical bonds with the oxygen. That's not an equal sign. It means the carbon and the oxygen are sharing 2 pairs of electrons, and the same with this oxygen over there. Here's our water molecule that we just discussed. Here's oxygen, molecular oxygen. This is O2, 2 oxygen atoms sharing 2 pairs of electrons. That's a double bond there. So and this is a silicon dioxide. So what we've got here is a great diversity of molecules, because we started with a great diversity of atoms, and they can link up and form chemical bonds in lots of different ways. Now you might notice there is a pattern in the way some of these elements are making chemical bonds, specifically the number of chemical bonds they make. Wherever you see a hydrogen atom, it tends to make just 1 chemical bond. So the hydrogen here is making 1 bond with nitrogen. The hydrogen here is making 1 bond with carbon. The hydrogen here is making 1 bond with oxygen, 1 bond with another hydrogen. On the other hand, oxygen atoms tend to make 2 chemical bonds. Take water. Here's the oxygen, makes 2 chemical bonds. Here in carbon dioxide, the oxygen is making 2 chemical bonds. Molecular oxygen, the oxygen is making 2 chemical bonds. And what about nitrogen? Nitrogen tends to make 3 chemical bonds. Here's 3 chemical bonds to hydrogens, 3 chemical bonds to another nitrogen. And what about carbon? 4 chemical bonds. Carbon is making 4 chemical bonds here. It's making 4 chemical bonds here. Now this is a pattern, and it has to do with the structure of atoms. Now we're not going to go into it in this course, but basically the idea is atoms tend to make the number of chemical bonds so as to fill up the outer electron shell, or the electron orbital. So if the carbon atom needs 4 electrons to fill its outer shell, carbon atoms tend to make 4 chemical bonds. Oxygen atoms need 2 electrons to fill its outer shell. Oxygen atoms tend to make 2 chemical bonds. We're not going to go into this in this course very much, but this is another example of this, the pattern that we find in chemistry, that atoms have certain structures, and the way atoms bond with each other shows certain patterns, and we'll lump that into our category of the law of nature. What it means, though, is that atoms don't just randomly hook up with each other. There are certain kinds of combinations and certain molecules that can form, and others are less likely to be formed. So we have a collection of diverse molecules that was produced by chemistry in space. Now these molecules have an interesting possible future. These are exactly the kinds of substances that we find on rocky planets like our Earth. So silicon dioxide and iron can be found in the rocks, in the crust of the planet, and inside the core of the planet. Here, these 4 gases, nitrogen, carbon dioxide, methane, and ammonia, were thought to be present in the early Earth's atmosphere. Later on, when living things evolved, and some of them were photosynthetic, those photosynthetic organisms released lots of oxygen into the atmosphere. And the water on our planet then was produced in space. So of course out in space it's cold, it would be ice out in space, but on a rocky planet within the habitable zone around a star, that water can exist as a liquid on the surface. So from stars to chemistry out there in space, we've set the stage for the emergence of rocky planets in our universe. Let's return to the story of the universe then. So now we've got a situation where stars have exploded and ejected all these heavier elements that are now forming molecules, and then gravity will condense these molecules into little particles of material, dust as it were. So this is a picture of the Orion Nebula. Actually, there's Orion, and this is the Running Man Nebula. And all this dust here, this is the stuff, these are small molecules and little particles of matter made of the heavy elements that originally were blasted out by previous generations of stars that went supernova. So when you see this kind of dust in a space picture like this, you want to be thinking about small molecules and little grains of rock, and there'll be ice out here. Well, ice, of course, is just water, frozen water. So this is the stuff that stars made, and it has great potential because it's this dust that can form planets. In this picture, then, we see sort of the later stages of solar system formation, the stars shining, and we've got well-formed planets here. But the idea is all this material down here, these little bits of rocks and dust and stuff, that's the kind of stuff that, under the influence of gravity, can form protoplanets, like what happened to our Earth some 4.5 billion years ago. So the dust in space, this dust, is the stuff you need to make a solar system. The hydrogen would be what you need to make a star, and the dust and the small rocky materials, all those heavy elements, that's what you need to make rocky planets. In fact, in the Horsehead Nebula here, scientists estimate that this nebula, just that nebula there, has enough material to make about 30 solar systems. Now here's a picture of our solar system, our star, of course the planets orbiting. Our planet Earth is in a very fortunate position. Scientists say that our planet orbits in the habitable zone. This is the zone where water can exist as a liquid on the surface of the planet. And why is that important? Because liquid water is one of the keys to life on Earth. Our cells are filled with liquid water, and that allows for complex chemistry to go on inside our cells. If the Earth were much closer, then the energy from the sun would evaporate all that water. And if the Earth were a lot farther away, the water would exist as ice. So with high chemical diversity, liquid water, and time, something amazing happened. Somewhere on planet Earth, perhaps deep in the oceans, 300 million years of experimental geochemistry produced cellular life. Now what you're looking at here, these are undersea hydrothermal vents. And a lot of scientists think this might be the greatest candidate for where did life originate? Where did life begin on planet Earth? These rocky structures have tiny little chambers about the size of cells where interesting chemistry is going on. Now imagine 300 million years of chemistry going on in these little chambers, and you can imagine more complex and more complex molecules forming, eventually assembling into cells. That's one of the current best ideas in modern science today. Here's an artist's rendering of this process. The rocky chambers, kind of like rocky nurseries, birthing out these little globes. These would be the first cells on planet Earth. They would have the capacity for reproduction and evolution. The idea, though, that chemistry can produce life, though that really does lead one to believe that we live on one strange rock, that a planet, under the laws of nature, produced life. But then the story doesn't end there, of course, because life went on to go through this evolutionary process. In the last 4 billion years, these simple cellular beings evolved into the millions of species that inhabit the planet today. And we'll study this evolutionary process, and there are patterns there. This is not just some kind of random process. There are patterns to how living things evolve. So again, we'll put that into the category, the basket of the laws of nature. Again, we see that new things are coming into existence. First, the origin of life from chemistry, and then new living things will emerge through an evolutionary process.